So if anybody has any objections to the fact that they're currently streaming on the internet, please let me know so I can shut that off. Okay, great. Well then in that case, everybody who is here today, welcome and thank you for joining. So since about the early 1970s, Moore's law has forecasted a doubling of transistor density in silicon roughly every 18 months to 2 years. And this densification of the transistors actually corresponds to exponential increases in computing power during this time. Now we know that no exponential trend can last forever, and so it'll have to slow down and stop eventually at some point. And in 2016, Intel actually announced to their investors that they were going to be slowing down the pace that they release their smaller process chips. Now, in order to continue keeping up with the still exponentially increasing demand for computing power, we have to look at certain like application side resourcefulness in order to do this. So in this dissertation today, I'm going to provide 2 life extension strategies for Moore's law. The first is one where we operate directly on compressed data without first decompressing it. And the second is to leverage highly parallel automata-based hardware coprocessors. So real-world data exhibits very regular patterns. So you can see in this building, the windows are not regularly placed, but rather are along this very strict grid structure. So this means that there is a much easier way that we can describe the placement of all of these windows other than listing them explicitly. And not only can we describe the building more succinctly in this way, but we can also answer questions about the building in this way. So for instance, if I wanted to know how many windows are on this building, if I was unaware of any sort of grid-like pattern, then I couldn't do any better than, say, counting linearly the number of windows. However, knowing that they're arranged in this way, I can just count the number of windows along each dimension, do a simple multiplication, and then much faster calculate exactly how many windows are on that building. So the advantages we get by doing a compression-aware approach are twofold. So the first is that we're able to get kind of an artificial extension to Moore's law, where in the case that we're operating on very highly compressible data, the compressed data can actually be logarithmic in the size of the raw data, which means that if we have now a polynomial improvement in the compressed data domain, that would correspond to an exponential improvement in the raw data domain. Additionally, these compression-aware algorithms have the advantage of just dealing with less data. So, for instance, if we could have a very data-intensive algorithm, which is disk resident, so it has to do a lot of disk accesses, and then by compressing the data and operating on that, we could actually get that disk resident operation to become a RAM resident operation, which would result in much faster runtimes. Now, towards this end, I'm going to be discussing, in my dissertation, I discussed 3 different data domains for these compression-aware algorithms. So the first is compression-aware algorithms for graph data. I discussed this in my proposal presentation. I'm going to skip it in the interest of time today, but it's in my dissertation if you'd like to read about that. And instead, I'm going to be discussing text-based data and geometric data. So the reason I've chosen these 2 data domains to talk about today is to provide an important lesson about compressions and compression-aware algorithms. So today, those who are designing compression schemes are most interested in dramatically reducing the amount of space that's required to represent data. So they're trying to optimize for compression ratio. The issue with this approach, however, is that, first of all, as you're trying to hyper-optimize for compression ratio, your compression algorithm takes more time. And additionally, as you have tighter and tighter compressions, the compression itself is more cryptic, so it's more difficult to do operations on that data. So what that means is that instead of designing compression schemes for the sake of compression, we need to co-design compression schemes with operations we'd like to do on those algorithms. So that might mean sacrificing a little bit of compression ratio in the interest of making it easier to operate on that compressed data. So to start out with, let's look at sorting a list which has been compressed using a string-based compression. So the string-based compression we're looking at today is one which compresses using a context-free grammar. So the string will be represented by a uniquely parsable context-free grammar. So a context-free grammar is a list of variables and production rules, so that you start with some start variable and you iteratively reapply the production rules until only terminal elements remain. And whatever string you end up with at the end, that was the string represented by that compression. So to use this to compress a list, what we're going to do is represent that list as a string of comma-separated values. And we'll see that if we take that list and compress it using a context-free grammar compression scheme, we're actually unable to run any faster than n log n, where n is the number of elements in the list. That is, the runtime does not depend at all on the size of the compressed data, but rather the number of elements in the raw data. So consider, for example, this structure of a compression for this list. So A0 is our start variable here, and A1 through AN will be variables representing exactly one term in the list. So this list will have n terms in it. So this means that I can permute this list by changing the order of the variables as they appear in that first production rule. The way I enforce that each of these variables is exactly one element in the list is their production rules must end with a comma, which is our list delimiter in this case. And now whatever goes before that comma here can be arbitrary, so we can use other variables in the context-free grammar to arbitrarily compress every term in this list. So because of this, we have all n factorial permutations of this list being arbitrarily compressible to exactly the same size, which means that we can use a standard decision tree-based argument in order to show that that sorting these will require n log n time. So what we've seen here is we've actually seen a mismatch between the compression-aware algorithm and the underlying compression scheme. So we were unable to get any sort of benefit by compressing the data first. So what this does is it motivates co-designing compression schemes with the algorithms we would like to run on them. That is, we need to develop algorithmically aware compressions in addition to these compression-aware algorithms. So in this next part, I'm going to be discussing an algorithmically aware compression scheme useful for point set compressed data. So for this compression scheme, we first observe that point set data in the real world is not randomly placed, but instead is typically the result of some sort of tiling, which causes these points to appear on roughly regular lines with a fixed interval between them. So now we can more succinctly describe these points by giving the equation for a line, an extreme point on that line, the interval between points, and then the number of points that are on the line. I additionally will discuss a lossy version of this compression scheme, where I don't require that the points fall exactly at regular intervals along this line, but rather I can perturb them by some small epsilon in order to round them to this case. And this small epsilon is actually an input parameter for that compression scheme. So here's a list of algorithms which I solve in a compression-aware manner. So this first one is convex hull, and the runtime of this is actually going to be the runtime of any out-of-the-box convex hull algorithm, except in terms of number of lines in the compressed point set rather than the number of points in the raw data set. Next is nearest neighbor, where given some input query point, the return will be the nearest point to that query. Then I have polytope membership, where a polytope is the many-dimensional analog to a polygon. So for this, for an input polytope, we will return the set of points that are contained in that polytope. And the runtime here is the number of lines in the compression times the number of faces that are within that polytope. And then I give two versions of range searches, which will return all of the points within a fixed either Manhattan or Euclidean radius of a query point. So I'm going to go into a little bit of detail on how exactly these range searches work, just to give you an idea for these algorithms. So in this case, we have our set of lines compressed point set. We have a query point, and then the circle represents the radius of the Euclidean range search. So in order to find the set of points that are within this circle, we're going to repeat the following operation per each line in the compression. We'll take the query point and find the distance of that query from that query point to the line that we're currently working with. And since we know this distance as well as the radius of the circle, we can compute the length of this chord where the line intersects that circle. And then from here in a constant time operation, we can trim the compressed line to be only the part that is that chord. And now this actually represents a set of lines compression of the points on that line within the radius. Now we can repeat this for all lines in our set of lines compression. And you'll notice here that this line, even though it intersects with the circle, no points fall in there, so we won't return anything for that line. So I implemented this algorithm and compared it to a KD tree implementation for range queries. A KD tree is a data structure. It's a traditional data structure that is optimized for nearest neighbor and range searches. And I found that for highly compressible data, I saw roughly the same runtime for my compression-aware approach as I did for KD trees in the case that the set of return points was 0 in that case. And however, even though my runtime was the same, if I assume the data was already in a compressed format, I've saved about 10 minutes of time that it took to decompress the data and then construct that KD tree data structure.
On how many points?
So I did a wide variety of points between like thousands to millions.
And it was always 10 minutes?
No, so this was kind of the median, middle of the road from the experiments that I did. And I did, the point set that I used was like a randomly perturbed grid in many-dimensional space, basically. So now the biggest advantage that we get from running this compression-aware approach is by the fact that this return is compressed data. So the KD tree algorithm, when it's returning its points, it has to return those points explicitly, so its runtime will be lower bounded by the number of points returned. In this case, since we're returning them compressed, the runtime is going to be lower bounded by the number of lines in the compression. So that means if we're returning lots of points, we get actually huge benefits in the compression-aware approach. And in our experiments, we saw up to like a 300-time speed up compared to the KD tree approach.
What was the worst speed up?
0. Yeah, so it certainly scaled, the speed up scales basically linearly with the number of points that we had to return.
You mean the speed up gets larger as you have more points?
Yes. Don't know what I said, but that's what I meant to say. Thank you.
What you said was ambiguous.
Okay. So you don't know what I said either. Okay. So in the case that the data was lossy compressed, since there's some uncertainty with where the points were in the raw data, there's going to be corresponding uncertainty in the response of the algorithm. So we'd like to bound and characterize that uncertainty. So if we're looking at convex hull, there's unbounded error actually in how many points could fall on the convex hull figure in the lossy compression-aware case versus the raw data. So that means there could be arbitrarily more or fewer points or vertices on that convex hull. In the case of nearest neighbor, the returned point could be up to 2 epsilon farther away in the lossy case compared to the traditional case. And then for polytope membership and range searches, what I've done is actually return the points in two different point sets. The first point set is all of the points guaranteed to fall within that figure. And we obtain that basically by shrinking the figure by epsilon. So for instance, we would move each face of the polytope inward by epsilon, or we would shrink the radius of the range searches by epsilon. And then the second point set is the points where we're not sure, there's uncertainty whether or not they actually were within the figure. So we obtain those by actually growing the figure by some epsilon. So expand the polytope outward or increase the radius by epsilon.
Back a second. Your error for your algorithm is the same as the error for the decompressed and then running the problem?
Yes. Yeah. So these are tight errors. Yes. So these errors are inherent to the lossiness rather than some artifact of the way that I run the algorithms. It's a good question. So the next technique that I discussed in this dissertation to provide a life extension to Moore's law is the utilization of highly parallel hardware coprocessors. So these coprocessors will sacrifice some generality of the problems which they solve in favor of being more efficient at solving other algorithms. So for instance, GPUs will achieve massive speedups through parallel floating point operation. And the architecture that I'm going to be discussing today is an automata-based architecture whereby these architectures will actually simulate non-deterministic finite state automata directly in silicon. The particular architecture that I focus on is the Micron Automata Processor, which was developed by the Micron Corporation. And in addition to simulating these non-deterministic finite state automata in hardware, it provides these two additional utilities for computation. So the first is Boolean logic gates. So these allow for transitions to be conditional on other transitions, basically. So you can see here that this state on the right will only become active in some cycle if on the previous cycle both of these states to the left were active due to the presence of this AND gate here. Additionally, it has these threshold counters which provide a limited notion of memory to the finite automata, where they have an internal count that can be incremented anytime there's an incoming transition on this line here, and they'll provide an outgoing transition whenever that internal count exceeds some reconfigurable threshold. So the first question that we'll ask about this is, what exactly do these additional utilities provide in terms of the computation power of finite state automata? So there's a pretty simple construction for converting threshold counters into gate and state equivalents. So I'm going to leave that out today. So really the only question that remains is, what role exactly do these Boolean logic gates provide? So to answer this question, I'm going to compare these automata with access to Boolean logic gates to a generalization of non-deterministic finite state automata called alternating finite state automata. So alternating for a non-deterministic finite state automaton, if there are two transitions emanating from a particular state, then that automaton will accept provided there exists a path outgoing from there which accepts. Now, alternating finite state automata allow you to additionally give universal restrictions. So you can have some states that are designated as universal states, for instance, this one here, and if there's multiple transitions outgoing from that state, we say that the automaton will only accept if all paths emanating from there will accept. So you can see that there's an intuitive parallel between alternating finite automata and AP-style automata which have access to these Boolean logic gates. For instance, in this case, this AFA will only accept if both of these paths will end up accepting due to the presence of this universal state to the left, and this AP automaton will only accept if both of these paths are accepting due to the presence of this AND gate. So it's easier to see this when you have linear automata like this with those cycles, but it turns out that these are equivalent models of computation, even in the case that you have universal gates or logic elements that are within cycles of the automaton. So the proof here is pretty deep and complicated. I discuss it in my dissertation if you're interested, but I am going to skip that. So alternating finite state automata as a generalization of non-deterministic finite state automata can actually be converted into NFAs with at most an exponential explosion in the number of states. That is, if I have an AFA with k states, I can convert that into an equivalent NFA with 2 to the power k states. So the conclusion here is that these machines actually still accept exactly the regular languages. So the corollary here is that AP automata 2 also accept only the regular languages. Now at first this seems a little bit pessimistic, that we have this new hardware coprocessor and all it can do is regular languages. However, that can still be extremely valuable if it's much better at computing regular languages than other architectures might be. So here's where we explore that. So a prior result has shown that you can simulate any regular language or compute any regular language in logarithmic time using a polynomial number of Turing machines. Or equivalently, you can compute any regular language in logarithmic time with as a circuit with a polynomial number of gates. Now this log and polynomial here are in terms of the size of the input string, but they actually say nothing about the size of the automaton required to compute that language. So we need to look at the the space requirements to see how efficient that AP architecture is going to be in terms of computing these regular languages. So it turns out that it's quite large. So if we have an alternate or an AP machine that has k states in it, then that could require up to 2 to the 2 to the k to the power 2 to the 2 to the k different or space in order to do that. So that actually indicates that because of this like nested 4 high exponential here, it can be much more efficient at computing regular languages or some regular languages than, for instance, an FPGA might be while using a circuit model or a CPU might using a Turing machine model. So now since we've seen that there are likely some problems that are more efficiently solvable on the AP, let's talk about some of those. So, so far, all the applications that have been discovered for automata processors have intuitively had this behavior of kind of a pattern matching operation, where you take an input string and you look for patterns in that input string, or try to identify patterns in that input string. So in order to broaden our understanding of the potential for these architectures, I would like to do exactly the intuitive opposite of that kind of operation. So instead of a pattern matching or a pattern finding operation, I'm going to be looking at a pattern obscuring operation. So for that, I'm going to be looking at pseudorandom number generation. A pseudorandom number generator is a deterministic algorithm which will take as input a small amount of random bits, truly random bits, and give as output a larger amount of bits which appear random. And by appear random, what we mean is that there is no polynomial time algorithm that can look at the output of that pseudorandom number generator and distinguish that from actually truly random bits. The way that we do do pseudorandom number generation on the AP uses a conversion of Markov chains to automata. So the idea is we're going to be simulating a large number of parallel Markov chains all at the same time as automata. So for instance, let's say that we wanted to simulate a biased coin. So here, this is going to be our automaton for a coin that lands heads with probability 1/3 and tails with probability 2/3. And the way that we achieve that is we make the proportion of symbols matching on each transition exactly equal to the probability that the Markov chain would take that transition. And then if we simulate truly random input to this automaton, it will transition randomly equivalently to how a Markov chain would. So now what we do is we take lots of these and run them all in parallel, sharing the same input. So that now, since all of these are sharing the same random input, each one is going to print out which state it's in after every single input, so that now, since each is sharing one input and independently printing out its current state, we have an expansion from the number of input bits to the number of output bits, which satisfies that property of our pseudorandom number generator. Now the issue is that since each automaton is deterministic, the entropy of the output can't be any greater than the entropy of the input, which means that the states that these automata are in are correlated in some way. And this can only succeed as a pseudorandom number generator if that correlation is obscure and hard to determine. So to make that or to satisfy that property, what we're going to do is actually generate each automaton itself randomly as well. So for instance, let's say that we're going to simulate a bunch of automata in this way for our pseudorandom number generator. So each automaton in this case is going to basically be a Markov chain for a 5-sided fair die. So each transition will represent one roll of a 5-sided die. So to generate this randomly, what we'll do is we'll take one of the states, for instance, state 1 here, and we'll do a random permutation of our symbol set to serve as the adjacency list of the outgoing transitions from that state. And now we can repeat this procedure for every single state in that automaton, and then for every single automaton that we're going to simulate for our pseudorandom number generator. And that gives us, this is our high-level overview for exactly how the pseudorandom the APPRNG algorithm works. So in this case, we're simulating M machines, each of which is going to have S states. And for the random input string that we use, we'll use the first chunk of that to build the machines by finding M times S random permutations, one for each state in all the automata. And then the remainder of our random input string will be used as the shared input among all of the Markov chains we're simulating. And as these Markov chains transition, they're going to print out which state they're in at every step. And then we can concatenate all of those together into our hopefully pseudorandom output string. So now the question is, how do we justify that this output is going to be pseudorandom? And there's two basic ways that we can do this. And which you use depends on what kind of application you're targeting for that pseudorandom number generator. So in the case that you're trying to use your pseudorandom number generator for, say, Monte Carlo simulations or other like practical uses, typically you use statistical tests to justify it. So there are some statistical tests that are out there that will look at input bits, and it will try to determine whether or not there's certain patterns that are overrepresented or underrepresented in those bits. And if the output of the pseudorandom number generator will cause the statistical tests to conclude this is random, then congratulations, your pseudorandom number generator is strong. So with this evaluation, this was done largely in collaboration with Jack Wadden. He actually took the lead on this project. So we began with the test UI01 test suite, which as far as we know was and still is the most robust set of statistical tests that are available. These statistical tests actually used about 1 terabyte of input data in order to conduct its tests. And we did find that some configurations of number of machines and number of states, which would cause APPRNG to pass all of the tests in that test suite. We also used this to try to optimize APPRNG to say what kind of throughput can we expect in practice. We compared this to the Phylox algorithm, which we identified as the state-of-the-art and high-throughput pseudorandom number generation. It's actually accelerated by a GPU to achieve 145 gigabytes per second of random throughput. And this algorithm will also pass all of the tests in the test UI01 test suite. So the projections for the first generation AP hardware will actually give us an upper bound of 437 about megabytes per second per chip of pseudorandomness using APPRNG. This is primarily upper bounded actually by the constraints on the reporting architecture for how it is that you get your output off of the board. However, if we assume more modern memory designs that are used to construct the architecture, we can see a lot better performance. For instance, if we're using DDR3, so modern DDR3 for memory, we can achieve up to 12.8 gigabytes per second per chip. And now since there's 32 chips per board, if we assume that the reporting architecture is no longer a bottleneck, we can actually achieve up to 500 gigabytes per second per board. If we use a hierarchical memory cube technology, we can actually achieve up to 28.3 gigabytes per second per chip, which across 32 chips is almost a terabyte per second of pseudorandom throughput. And all of this, by the way, is achieved at a 6.8 times better energy efficiency per bit than the Phylox algorithm. So the second way that we could justify this algorithm as a pseudorandom generator is using a hardness assumption. And this is used whenever you're trying to use a pseudorandom number generator for the purposes of cryptography. So what we do is we say that any algorithm D, which could distinguish truly random sequences from the output of your pseudorandom number generator, must be able to solve some problem that we believe to be difficult. So the particular problem that I'm going to be looking at for APPRNG is one that's based on automata learning, where basically I'm saying that that I'm requiring that there is no algorithm which can efficiently learn how many states are in some sort of black box automaton by observing a random walk. Or more specifically, that it's difficult to distinguish a random walk on a large automaton from a random walk on a small automaton. So we can actually take all of the parallel automata that are in APPRNG and combine them to an equivalent larger automaton using a standard technique called a cross-product construction. So we can take these and then combine them to this gigantic automaton. So there's a multiplicative explosion in the number of states when you do a cross-product construction. So since I started out with 4 machines, each of which had 5 states, this large automaton that simulates the combination of all of those is going to have 5 to the power 4 states. And now a random walk on this automaton will be identically distributed to the output of APPRNG. So our distinguisher for the pseudorandom number generator has to be able to tell the difference between the output of a random walk here and then truly random input. So I'm going to model that truly random input also with an automaton. And in this case, if we take just one of the automata that's run in parallel for APPRNG, that actually serves as just a random permutation of the truly random input. So that actually does not affect the entropy of the data at all. So therefore, the truly random case can be modeled using just a single one of the 5-state automata. So now the question is, can there be an automaton to distinguish a random walk between these 2 machines? Or can we have an algorithm which can learn how many states are in the machine by observing these random walks? So to justify that this is a hard problem, we need to look at a history of these types of automata learning problems. So the first result in automata learning was in 1978, so this is almost a 40-year-old problem. So a lot of people have worked on this. So Dana Angluin showed that learning from examples is NP-complete. So by learning from examples, we mean determining the number of states and the topology of an automaton, looking only at strings that do versus do not belong to the language of that automaton. Now, she showed in 1987, in her famous L-star algorithm, that instead of learning from examples, if you allow the learner to select input to test on the automaton, then you actually can efficiently learn the automaton. And by efficiently, I mean polynomial time. However, this required a reset capability where the learner could instruct the automaton to transition back to its start state. In 1987, Revest and Shapir were able to remove that reset assumption. In 1993, Freund et al. Showed that you could learn by observing how the automaton transitions on random input rather than on chosen input. And then in 1994, Kearns and Valiant gave a more specific version of the 78 result, which showed that even if you assume that your automata are acyclic, then learning the automata is as hard as breaking RSA. And this is still a problem that is actively worked on today. Just in 2015, Dana Anglewin improved upon this 1993 result. So the fundamental flaw that all of these results have is that they all require the learning algorithm to look at the input given to the automata, which is behavior that's not allowed for the distinguishers between a pseudorandom number generator and for the algorithm to distinguish the output from the pseudorandom number generator from truly random output. And this is in spite of the fact that there's a clear trend in making weaker assumptions about the nature of the input to the automata, where, in my opinion, intuitively, not requiring to look, or having an algorithm that doesn't require the input to the automata at all is the weakest assumption you could make. So that's kind of the best way to learn these automata. And all of this is in spite of the fact that two of these individuals are Turing Award winners. So Ron Revest and Leslie Valiant are both Turing Award winners who have looked at this problem. So now that we've justified that APPRNG seems to behave as really a high throughput, strong quality pseudorandom number generator, I'm also going to show, so that another contribution that this pseudorandom number generator has is that it enables a larger class of problems to be accelerated using automata architectures. So that is any algorithm which could be modeled as a parallel simulation of Markov chains can be highly parallelized on automata processors based from the APPRNG result. So an example of such an application is automata-based Bloom filters, which I'm going to be discussing today. So a Bloom filter is a set membership data structure where there are two queries that can be performed on this data structure. The first is insertion, which will add an item into the data structure. The second is a containment query, which will return true provided that given element had previously been inserted into the data structure. Bloom filters are able to do both operations in constant time. And the way that it does this is by allowing for a small probability of false positives. That is, for some containment queries, there's a small probability that the data structure will return true, even though the item had not previously been inserted into the set. So the way that traditional Bloom filters work is they begin with a bit vector initialized to all zeros and a set of hash functions where each hash function will map to an index in this bit vector. So now let's say that I want to use a Bloom filter to keep track of my set of friends. So to insert ka into my Bloom filter, what I'll do is run ka as input to all of the hash functions in my list and look at which indices they map to, and I'll set all of those to a 1. And then I'll repeat this for all of my other friends in my list of friends. So now let's say that some mystery person walks in the door. And I want to know, is this mystery person one of my friends? So what I'll do is I'll take this mystery person, Batman, and give him as input to all of the Bloom filters. And then look at all of the bits that are mapped to, I'll give it as input to all of the hash functions. Now I'll look at all of the bits that are mapped to by these hash functions. Now if all of them are 1s, then I can conclude with high probability, not certainty, but high probability, that Batman is my friend. If, however, there is at least one hash function which mapped to a 0, then I know with certainty that Batman is not my friend. Because otherwise, if Batman was my friend, I would have set that bit to a 1 when I inserted him into the Bloom filter. For automata-based Bloom filters, we're going to consider automaton acceptance as equivalent to a Bloom bit being a 0, and automata rejection as a Bloom bit being a 1. So we'll start out with a large number of parallel automata, which were constructed as simulations of a Markov chain. And in order to insert ka into my list now, I'll run ka as input to all of these automata. And any automaton that accepts, I'm going to remove from my set of automata. Now I can repeat this for every person in my friend list, removing all accepting automata, so that now if I have some mystery person who walks in, so if Batman walks in order to determine whether or not Batman is one of my friends, and this is a really weird time for you to walk in. So in order to determine whether or not Batman is one of my friends, we'll run Batman as input to all of the remaining automata. And if any of them accept, then I can conclude with certainty that I am not friends with Batman. Because otherwise, when I inserted Batman into the Bloom filter and that automaton accepted, I would have removed it. If, however, I run Batman as input and none of the automata accept, then I can conclude that with high probability I am friends with Batman. So now we need to look at how many automata we need to simulate in order to mimic the behavior of traditional Bloom filters using this automata-based approach. So if we have a Bloom filter where the bit vector had n bits and we inserted n items, a prior result actually shows that the optimal choice for number of hash functions is m divided by n times the natural log of 2. So we're going to pick these parameters and try to show how many automata are needed to get the same false positive rate as traditional Bloom filters. And based on the construction that we have currently, that's going to require about 1.4 machines per bit in the Bloom filter. Now, after we insert all of the n automata, we'll have about 0.7 remaining, which is how many we need to simulate for every query. So now in this dissertation, I provided two basic life extension strategies, one through hardware and one through software. So the software approach utilized compression-aware algorithms where we designed algorithms to operate directly on compressed data without decompressing it first. And we looked at both geometric and text data. We looked at lossy versions, or lossy compressions and lossless compressions both. And we also talked about how to co-design compression schemes with compression-aware algorithms. In the hardware case, we looked at automata processors, where we showed that they seem to be actually fairly efficient hardware for simulating regular languages, for computing regular languages. And we expanded our idea for the problems that could be solved by automata processors by providing pseudorandom number, a way of doing pseudorandom number generation, which intuitively shouldn't have worked. And finally, we gave an application for that pseudorandom number generator result being automata-based Bloom filters. So since these are meant as life extension strategies for Moore's law, we now have to ask, what is the longevity of these strategies? When are we going to hit some sort of brick wall for these? So for the automata processor approach, basically my hypothesis is that this will add further, just a few more iterations of transistor densification within the hardware. So it kind of pushes forward Moore's law by some amount. For this software approach with the compression-aware algorithms, the benefits we can get here, I think, is much more open-ended. So the speedups that you can get are basically dependent on your application, and they're only limited by the entropy of the data that you're trying to deal with in your application. So in terms of what to do next, so where can we look at to go further? So from the compression-aware algorithms approach, we could start to look at compression-aware data structures as well. So that is, we have a data structure which structures compressed data. So for instance, I talked about KD trees as a way of, as a data structure for classical point set data. Well, maybe we can have a KD tree for compressed data and do even better than the queries that we already had. We could also combine automata processor computation with compression-aware algorithms. That is to build automata-based compression-aware algorithms. So some compression schemes can actually be modeled as, can actually have their decompressions be modeled as automata, which kind of intuitively means that we should be able to do something on automata processors. Additionally, there's been a lot of research already on compressed pattern matching, so doing pattern matching on compressed data. Again, it seems like an intuitive fit for automata-based designs. So as an example, first application we could look at is doing compressed pattern matching on Huffman-coded data, because Huffman trees could actually be modeled as automata. Finally, we could look at how to use lossy compressions accelerated with imprecise hardware. So if we're using a lossy compression, we already have stated that some amount of uncertainty or error is acceptable. So rather than limiting that only to the compression, we could allow for some error and uncertainty in the hardware. So we could have more efficient hardware that has small errors to operate on lossy compressed data. And we could even combine this potentially with automata-based architectures by saying that the automaton is both an automaton and a Markov chain simultaneously, where each transition maybe has a small probability of a false positive or a false negative when transitioning. So now we can use that imprecision to simulate Markov chains or to operate over this lossy data. Since we've asked all these open questions here today, I'd like to open the floor and see if anybody else has any open questions for me. So if you guys don't mind, a while ago I attended my older brother's PhD defense. And much to his disappointment, I quickly raised my hand to ask him the very first question. So I promised him that he would have the opportunity to torture me in a similar way. So he's joining us on Facebook right now. So if he has, so Robbie, can you check if he's asked any questions?
Is this Justin?
Yeah, this is Justin.
I asked him for questions earlier, and he said that he would unhappily take his offline and yield the floor to the committee.
Okay, well. Yes.
Early on, you had stated that some compressions resulted in logarithmic size data.
Yes.
All the compression schemes I'm aware of are linear or in a very few cases polynomial. Do you know of a logarithmic compression algorithm?
So for instance, you could look at run length encoded data. So if you had a run length encoding, you could say it's just a bunch of, let's say that we had a string that was 105 A's in a row. You could say 105 A's so that the size it takes to represent that A is a constant in this case. And now all you need to do is represent that number, which you can do in log space.
And yet, in practice, RTL usually gives us a constant compression.
Yeah, so practice is different from theory, right?
Okay.
So hypothetically, for super highly compressible data, you can actually get logarithmic size compressions. That's even the case for the set of lines compression scheme that I give here. That's also the case for the context-free grammar compression scheme. They're both entropy, or I'm not going to say that the set of lines is entropy rate because I haven't proved that, but the context-free grammar compression scheme, in the best case, is actually an entropy rate compression scheme. So you can get up to logarithmic space in terms of the original raw data if you're lucky. Now the challenge of this is actually that finding the optimal compression for context-free grammar compression schemes is an NP-hard problem. But a lot of dictionary-based compression schemes can be modeled by these. You can think of them as approximations of that. Yes?
So you talked about the algorithm compression scheme matching. Well, and I haven't seen the dissertation, so you may have answered this there. But So I didn't see suggestions about how to do that matching as opposed to just an observation that one was bad because of this.
Yeah, so I don't have some sort of falsifiable rule for how to do this. It's more of an intuitive kind of thing. What I found in my experience, however, is that it tends to be much easier to do these compression-aware algorithms on compression schemes specifically designed for the type of data that you're dealing with. So, for instance, the geometric compression scheme took points and turned them into another geometric thing, being lines. For the graph compression schemes I look at, it takes graphs and converts them to other smaller graphs. So that's kind of the first place to look based on my experiences. So a lot of times what people will say to me is like, oh, well, can't you just take your data set and do a standard string compression and use some string compression-aware algorithms that people have already done? And it's like, well, no, you can't. For instance, this sorting example, I think, is a very compelling instance of that. Yes?
Your automata processor conversation, you mentioned there was some limited sort of counting, which
Yes.
you never mentioned again. Does this also not change the expressivity of the grammar?
It does not. So the reason for that is that the value of that threshold is basically a compile time decision. So from the perspective of the automaton, or from the perspective of the length of the input, that is constant. So if you had some other design where with the input you could change the threshold, then it would become more expressive, is a corollary to that.
More questions?
Sorry.
Yes.
So you said that the example data you're running things on was a perturbed grid.
Yes.
It seems like there's a far more efficient compression algorithm to perturb grids than lines, i.e. grids.
So when I say perturbed, the actual grid axes were perturbed. So vertical line 1 would be perturbed differently from vertical line 2 and so on. So they would have eventually intersected at some point.
How much perturbation did you allow?
Just a very small epsilon. So it was small enough that they didn't intersect in the points that we were looking at. We varied that for some experiments and found that it didn't really matter.
How much did you vary?
So I think that we did from like 0 degrees to 45 degrees or something like that. And for 0 degrees, there are cases where we could accidentally get into a situation where the KD tree data structure got what I consider to be an unfair advantage. But between 0 and about 45 degrees, we didn't see any difference.
If you're only doing small perturbation, isn't there there's still structure there then?
So basically the result of this is going to be that every quadrilateral that is a grid cell will be a random quadrilateral. So there is some structure there, but it's hard to see how you could express it as, say, a tiling or a tessellation like you would have in a grid, because every quadrilateral is going to be slightly different.
But they're close to the original, right?
They are. So let's see. So to think about this, since each line was kind of perturbed by a random amount, it's hard to imagine how we could express it more simply than saying it's a grid with these perturbations, right? Where each axis has these perturbations. So if each line was perturbed randomly, then it's hard to say it's a grid where each line was perturbed in this way. So each vertical axis was perturbed in this way. So the horizontal axes were not perturbed at all. It was only the verticals in this case. So if we said that the whole thing takes the structure of a grid where each vertical axis was slightly adjusted, then it's hard to see a way that you could describe that more succinctly. Because even if you could say it's a grid with these modifications, it seems to me those modifications would be basically the same as describing the perturbations of the vertical lines.
But if it was a small perturbation, wouldn't you be able to look at each line and see where it was in the original grid?
Wouldn't I be able to look at each line and see where it was in the original grid? I'm not sure I'm following.
So you had grids, you had a grid before, like a box, okay?
Mm-hmm.
All right, then you perturb each line. But since the perturbation is small,
Mm-hmm.
you can recognize that it's part of where it was in that box.
Okay, so I could recognize where, like, basically what index, what two-dimensional index that box was into the grid. Is that what you're saying?
Yeah.
Okay.
Does that give you any more help? Does that help you?
Intuitively, I don't think so. So, like, in order to determine, like, how far up it, let's say we wanted to determine how far up. So, what was the y-axis of that index? Let's say. Then, to determine that you would have to try to figure out what the perturbation was for that, and then look at the angles basically to determine how far up it went. But it seems to me that you would still need to look at, say, all of the available perturbations, since they were random, in order to do that. Are you satisfied?
We'll say yes.
Oh, okay. Yes.
You said you showed us, this audience, the details of the proof back on the sorting algorithm, I think. About the one proof in your dissertation, right?
So the proof in the dissertation about the sorting algorithm. So if I go back to that, so that's actually the same proof that I summarized here.
Right. So was there anything interesting that came out of that proof in the mechanism? I mean, in the steps that went through the proof? Did you have any aha moments, or this, that, and the other that were interesting in that proof, or was it just crunching through the steps?
So basically the takeaway that I got from this proof is that a compression scheme has to operate differently, or has to so in order to get any sort of benefit for the algorithm, you need to be able to identify some sort of heuristic for that algorithm that meshes well with the assumption that of the structure of the data that the compression scheme exploits. So basically, the context-free grammar compression scheme doesn't exploit any structure in the permutation of the list, but instead just the ordering of the characters in the strings. So really, you need to say that the assumption of the structure underlying the compression is somehow related to some sort of heuristic you can do in order to implement that compression-aware algorithm.
More questions? If it's okay, the committee would like to ask some questions in private.
Well, I'd like to ask a question.
Okay.
So, let's see. I'm going to focus mostly here on the pseudorandom number generation. Are the random inputs that you provide as the input string to the APPRG output, are they, can you think of them as being like a seed in other?
Kind of. So the issue is that with this, so the way that a lot of other pseudorandom number generators will work is that you have a small amount of randomness as a seed, and you kind of update that seed to be different over and over and over again. And at some point, that seed is going to repeat its value. So it's harder to identify what a seed might be for this, because we kind of just do a once and done with all of the pseudorandom input that we receive. So we kind of use it and then dump it.
So how do you generate them? Where do you get them from?
So random input is actually very difficult to come by. I think that just a few weeks ago, actually, NIST set up a website where you can go to get random inputs. So they have some sort of quantum device, and they can sample from that quantum device, and you can request randomness, and they'll respond with true randomness. That did not exist at the time that we were doing these.
So how do you do it?
So what we did is we actually used the Phylox algorithm as input. So since for pseudorandom number generators, the output should behave as randomness, you should be able to bootstrap to a certain extent pseudorandom number generators. So we actually use the output of the Phylox algorithm because it's a very high throughput pseudorandom number generator known to pass all of the statistical tests already. And using Phylox instead of true randomness should only hurt us. It shouldn't help us at all to use that.
But related to Kevin's question, so I think that algorithm must have a seed already.
Yeah, so that algorithm does have a seed.
Right.
So, how much can you reduce the amount of input relative to the amount of output that you generate? Basically, how much random output can you generate per bit of random input before you lose?
I don't have that number off the top of my head. I have some expressions for this, but I think that for like the optimal throughput, I want to say it was somewhere around like 10 times or something like that, if my memory serves me
So you've
correctly.
analyzed this?
Yes, we have analyzed this.
Was it in the dissertation?
I believe so. I'll have to double check.
I think it's worth including, and I apologize.
Yeah, I know that we did that. It's in the paper where we do the analysis.
That's what I thought, yeah. I apologize if I missed it.
It's possible that I accidentally excluded it from the dissertation, so I can add that in for sure if I did, and I apologize.
So, on FPGAs, you can run an automata simulation, basically, and it's very efficient, as Ted has shown. Which gets me wondering whether this would be a good random number generator for the FPGA, except that it seems like FPGA PRNG is using techniques like linear feedback shift registers and so on.
Okay.
Can you talk about can you help me think about how to compare those?
How to compare linear
Efficiency.
feedback shift registers?
And that whole family of circuit-based
So
communication
I'm so all I can really say about linear feedback shift registers is that there have been some papers published that that indicate that those are pretty easy to break, actually. So for instance, those aren't going to be useful for cryptographic purposes. They actually have a very small what they call stretch, which is the difference of the input size compared to the output size.
Sorry, mate, to interrupt, but no, this is a complexity, a big O kind of argument. I mean, you can have, linear feedback shift registers with polynomials of arbitrary size, and at some point, when you're at the size of the universe, it's going to be truly random. So I'm not sure I understand what you're saying. So because the question I think Kevin is asking, what would be the size? I mean, that's asking the question a different way. What would be the size of a linear feedback shift register or of a polynomial that would give you the kind of the equivalent randomness
question.
or the equivalent randomness of your solution, I guess.
So that is not an analysis that I've done to compare how linear feedback shift registers or other approaches compare in terms of the stretch, if that's what you're asking.
Yeah,
Or how much space they would require to
right.
get.
There is a direct. I mean, it's not the the ones that are being used for practical purposes have the short stretches that you are mentioning because they are good enough, and so it's a trade-off.
Yeah, so I'm not exactly sure how they compare. I haven't done that analysis.
Changing gears a little bit, in your list of publications, I don't think you listed a paper about the algorithmic efficiency of automata processing, AFA, and so on.
So I'm kind of so I've been struggling a little bit with exactly how to present that work, because I basically with one of my collaborators did some proofs only to find out after the fact that those proofs had been done about 30 years ago. So really what I've done is I've kind of taken these prior results and assembled them together to make a statement about this hardware, but there's no novel theoretical results in there. So I've toyed with the idea of presenting this as maybe a survey paper, where you can say here's a survey of some theoretical results as they apply to these hardwares, but I'm still kind of developing that idea.
Okay. So if you were going to extend the automata processing architecture to be more computationally powerful, while still maintaining many of the benefits of the specialization, what are some of the extensions that you would make?
So one extension you could look at is trying to find a different counter design. So if you have a counter design, as I mentioned in reference to one of Luther's questions earlier. So if you had a counter design where the threshold could in some way depend on the size of the input, then that would give you something beyond regular languages in terms of what you could compute. So an example of something that you might do for these types of counters is, instead of saying there's an internal count and then a pre-configured threshold and you have a way to increment it, you can instead say that there's a way to increment the counter or decrement the counter, and it will always provide an output transition whenever the count is exactly 0. So in this case, you could use that as some sort of analog to a stack in an automaton. So that would actually give you real memory rather than this approximation of memory. So that would probably be the first place I would look. That brings up some challenges though, because it's hard to maintain this illusion of non-determinism for these counters. That when you have different parallel paths through the automaton or something, for traditional push-down automata, you typically have also non-deterministic counter states, which is not something that you can maintain.
Can we? And again, I'm very uncomfortable with the term non-deterministic that everyone is using in this field.
Sorry.
No, but what does that statement mean, that you have non-deterministic?
So with an automaton, for instance, if I have a state and I have 2 outgoing transitions which match on the current input character, we move into both states at the same time. So you can think of this as kind of a mini worlds approach to computation, where you could say that there is one universe where we went to the right and there's a parallel universe where we went to the left. So that's what we mean by non-determinism.
No, I understand that, but what does
so in the case that we had a stack on our automaton, so like one of these increment decrement counters, if we're using this parallel worlds approach, when we split off, we want to also split the counters, so to speak, so that if the right path increments the counter, it doesn't also increment for the left path.
So why isn't that a problem with the current AP architecture?
I would say that it is, actually.
But we have yet to run into a case where it is.
So I think that might be that a factor of the fact that we haven't utilized the non-determinism super well, and also utilized the counters. We've more used parallelism with counters rather than non-determinism with counters.
It'd be interesting to try to come up with a meaningful example where the current API architecture actually fails because of this. Because then I think that'd be instructive on whether you really need a non-deterministic up-down counter, or whether you can get away with basically cheating.
Yeah. So for a lot of these questions about like, well, why haven't we run into problems with this yet? Part of it's because it's still kind of new. So we're still kind of like coming from the perspective of what can we do on this. So there haven't been very many people who have come along and have said, what can't we do on this, for instance. So I can give some ideas for types of things that might be impossible with this type of architecture, but it's hard to identify specific instances of that because that's just not the mindset that we've come up with so far, because that's not there's so much low-hanging fruit in terms of trying to find things that are possible compared to really strongly identifying things that aren't.
But in your example, so you somehow assume that the counter is necessarily at the, outgoing state. If you push two counters to the, it doesn't matter where you have that state, right? To the outgoing, then you don't have the problem anymore, right?
But I think the issue is you want to maintain you have some counter state.
Right, but you have them. Well, yeah. But again, you fork the counters themselves to the next state.
So you might be able. So there's a couple problems with that. One is you would need to do this dynamically, because what if you had a loop and you went back to that state? Now you have to fork again. So you would have to be able to have a large number of counters and a way to basically copy the counter state from one counter to another one. There was another one that escaped my mind. Another issue that escaped my mind.
No, it's fine. Yeah,
so moving on. Yeah. Okay, so that's one. What else would you extend? Sort of a practical, meaningful extension in the computing power of the API.
So another one would be probably more gates are going to be more useful. So this 2 to the 2 to the k to the 2 to the 2 to the k expansion basically assumes that you can have one gate per state in the automaton in order to get that. And right now that's far from the case. The Boolean logic gates are a much more constrained resource than the number of states. So I think up to that point, up to the point of having an equal number of states and gates, we'll see benefit. Theoretically, we should see benefit for some problems, for more problems, that is. So more states is always going to be useful. Like whenever designing this, I think that priority one for these automata-based designs is let's get some more states in there. And I think priority two should be try to get as many gates as we can up to the number of states that are there. And each Boolean logic gate is going to be more helpful with this. So if you can't get up to the number of states, more is still going to be better. Yeah.
Okay.
Go ahead.
So I have a question. So you use a parallel automaton to generate a random number, right? Parallel. So from your presentation, you assign a different subset to the different automaton machine, right?
I assigned different, in order to construct the machines?
Yes, yes.
Yeah, so in order to construct the machines, what I did is, so in the example I gave here, the alphabet size was the same as the number of states in the automaton. So what I did is I randomly permuted the set of symbols in the alphabet.
Yeah, so if you have a large number of the machine, automaton machine, so how to avoid the simulation, the situation that two machines have two similar subset?
Yeah, so certainly if we have enough machines, there are going to be two machines that transition in exactly the same way every time. That's unavoidable. So it can that doesn't harm the pseudo-randomness necessarily if it's still hard to detect that for however many inputs we simulate on there. So we're going to build the machines and then use a bunch of symbols to run the automata. So it could still be very difficult to detect this kind of situation where you have these two things that are always the same.
Do you have some algorithm to assign the single site in a smart way, or?
We've thought about that. We haven't really pursued it, but we have considered that might be a possibility, that instead of randomly generating the automata, there's some procedural way that you could do that more efficiently. It's hard to tell what that might be, so we've looked at it a little bit, but haven't made much progress on it.
So you have some evaluation result for the AP-based random generator and comparing with the GPU. So does this this number come from the real hardware or just?
Yeah. So that was. Sorry. Which one? The GPU result was actual hardware. That was an experiment. Our result, the only part of it that was experimental was the running of the statistical tests. So that was experimental. However, the performance was projected, not experimental, because we don't have completely fully functional automata processor hardware.
Yeah. So do you think there's some theoretical limitation that, because they proposed this automata architecture many years ago, but they haven't have the fully function chip yet. So do you think there's a theoretical limitation there, or it's just a manufacturing issue?
In my opinion, it's the latter. I think that it's kind of just been a rocky road for the company in getting this all together, rather than being so, at least for my limited understanding of architecture design, that's definitely not my area of focus. However, my understanding is that it's not some inherent issue with the idea of the architecture, but rather it's been challenges in the particular implementation choices.
So the last question I have is, you propose to use to apply your method to Huffman encoding or decoding, right?
Yes.
So, but I think the difficulty is the Huffman compression algorithm is variable length algorithm. So for the automaton machine, they just accept the symbol with the fixed length, 8 bit every cycle. So how do you have any idea to deal with the variable length symbol?
Yeah. So I have a backup slide. This is a Huffman tree. So there are analogs to these Huffman trees, which will compress at a byte level rather than a bit level. So there is prior work on that. So instead of saying that you have a sequence of bits to represent things, you have a sequence of bytes. So each of these transitions will occur on a byte. So in that case, like, yeah, they're variable length, but they're still in bite-sized pieces, pun intended, in order to drive the transitions on this tree. So I don't think that, so basically the idea, the kind of intuitive idea I had for how you could do this is that you would have to have each transition of the automaton kind of substituted with one of these trees. So that once you got to a leaf in the tree, that's when you would try to trigger what the next transition in the automaton would be.
But you need a decoding step to decode the bad symbol to a bit-based symbol, right? To
I'm not sure I follow. I'm sorry.
So for this structure, you will accept 1 bit or 1 byte.
So for this structure, the way that this structure would be traversed in the case that we were doing a byte level Huffman coding is that each byte would be a transition in this tree. So what I was picturing these automata would look like is that, let's say that I had a state that was up here and a state that was down here that should transition on a B. So in that case, I would have this tree where I would have whatever symbol was here, whatever symbol was here, whatever symbol was here. I see that's a B, so now I jump to that next transition. Does that answer your question? Okay. And in that case, the width of this tree would not be of width 2, but it would be of width like 256.
Yeah.
Okay. I have a couple of questions. So my first question is very kind of global in general. So if I look at everything that you've done, the software, the hardware, the RNG, the KD trees, you have taken, you are comparing, some new algorithm that you came up with some old algorithm or some solution, but the actual, outputs of your solution are not the same as the conventional. For various reasons, and again, each example will have a different reason why that is so. But I think, without exception, that's true. That you are kind of computing something slightly different, but then you are comparing some figure of merit. You are comparing performance, area, whatever. But you are not comparing the the kind of the accuracy, or I'm not sure how to call that, and I want your comments on that. And because again, if I look at at many other things that engineers do, including homeworks and exam results, if you come up with a slightly different answer, then it might not be okay. And when is it okay? And how do you decide? And why is it okay in all the examples that you've been using? So
first of all,
I'm asking, right?
Let me verify first.
Okay.
So if let's say that we go back to the compression-aware algorithms, and we're looking at the set of lines compression-aware algorithms. So I assume you're referring to, for the return data is compressed rather than raw data.
No, even after you decompress, if you look at the actual number of points, the exact, the identity of the points may be different.
So that's only in the lossy case.
Even for the
in the lossless case, the points that we return should be the same points that we started with.
No, but are they the same as if you would use the KD tree or something?
Yes. Yeah, so they're algorithmically equivalent. So the KD tree is a data structure.
From your.
I apologize for that.
Okay.
But yeah, the KD tree data structure does nearest neighbor and range queries, and nearest neighbor and range queries, that's a problem, not an algorithm.
Sure.
So they're an implementation for that problem,
right.
And I provide an alternative implementation.
No, I totally understand. But so you are saying that those two implementations are actually.
Yeah, so they both solve that same problem.
Okay.
So they're equivalent, yes. They're not equivalent in the case that we have lossy compressed data,
Right.
It would solve it equivalently to how the KD tree would in the case that we lossy compressed then decompressed.
Right. So okay, but loss. Yes, I understand. So so yeah, maybe my statement was a little bit more general, and yeah, but I still think that in a large part your solutions are in some sense approximate. Let's use that word. PRNG.
So, well, there's nothing that's not an approximate solution for pseudorandom number generation. So it's unknown whether or not a pseudorandom number generator actually exists. So if you could prove that one existed, then you prove that P does not equal NP. So every single solution to pseudorandom number generation is actually approximate. And Bloom filters are a very old and well understood and respected approximate data structure. And I behave I match the false positive probability. So in the constructions I use, I actually do exactly match the false positive probability in expectation, at least, of Bloom filtering. So that is approximate, but I am not approximate beyond its approximation. And its approximation is already an accepted and useful thing outside of this dissertation. So for instance, Bloom filters are used for doing things like antivirus detection, where you can take a bunch of packets that are coming in from the web, and then run a Bloom filter, or run these through a Bloom filter which has been set up with a bunch of known viruses already in it. And then you can look to see, is this in my set of known viruses? So since false negatives are impossible, if it passes, then you know it's safe very quickly. Whereas if you get a hit where it says, where the Bloom filter says that has been inserted, that could be a false positive, so you can take some more time inspecting that. But it's still a very fast way of weeding some things out. So that approximation is well understood and well respected, and I match their approximation.
But even there, so okay, so let's go a little bit in that direction. So you have these hash functions for the conventional Bloom filter.
Yes.
And then you have your automata for your Bloom filter with PRNG and all that.
Mm-hmm.
I'm pretty sure that statistics has more than the false positive rate. It has all kinds of other
yeah. So the exact distribution of
exactly.
false positives that I'll have
Right.
is different.
Right.
From Bloom filters.
Right.
However, in none of the prior art that I've looked at for Bloom filters was that brought up. So I didn't see any prior art where they said Bloom filters the distribution of false positives for Bloom filters has this nice property. So I took that as evidence that people were mostly concerned with how they behaved in expectation rather than the distribution of how they behaved.
Right, but it's not a very strong argument from a theoretician. Okay, so you are pushing back, and so you think there is no problem with any of these,
I think that there are some points to be brought up, especially for the Bloom filters, and I do bring those up in the dissertation. But I characterize some of the ways that it will behave differently from Bloom filters, even though I match an expectation. I don't think that there's any issue there for the compression-aware algorithms I talk about, and I don't think that there's any issue for APPRNG.
Okay, another issue. So you have the equivalence of the AFA and the NFA with the AND.
Mm-hmm.
And I found that weird the way you put it. So you said, okay, here's an AFA, and here is the NFA with the AND gate. And then you said, I'm not sure how you said they are equivalent. You said that...
So the idea is that both this upper path and this lower path have to be successful.
No, I understand
Okay.
how you go from AFA to the right. I'm not sure the argument that they are equivalent. you know, that you can represent an AFA like the one to the left with the, you know.
Yeah, so I omitted the specifics of that proof.
So you have a proof for that?
Yeah, and I talk about that in the dissertation. That's
Okay.
actually an old result. That was done
Okay.
in the 90s, I think.
Okay.
So I summarize that old
okay,
result. in the
Okay,
dissertation.
in the interest of time, sorry. But how about the fact that on the AP that can be more than an AND gate? It can be, or it can be.
That turns out not to matter.
And that's in the proof too?
Yeah, yes, that's in the proof too.
Okay.
That this could be like an arbitrary lookup table, basically, attaching to an arbitrary number of states, and it still works.
Okay. Okay, I think I have one more, just one question. Let's see. Maybe I'm done. I'm done.
More questions? And if you don't mind us having an executive session, I